Okay, so this is part 2 of the Homework 8 review. I'll go through the justifications of these a little bit more quickly than in the first part, and ultimately the full solutions with justifications will be posted. Okay, and be sure to read along with me and make sure that you're capable of reading, growing increasingly capable of reading these and making sense of them. So the first one says, for all x, if x is stronger than the queen, then x is identical to the king. That's quite obviously true. If we approached it formally, we'd say everything that's not stronger than the queen makes this true by virtue of making the antecedent false. And there is only one thing stronger than the queen, namely king. And so therefore, king is in fact identical to king. Okay, number 2, for all x, if x is light, and it's not the case that x is taller than x, then x is the pawn. All the dark pieces make this antecedent false, and hence the conditional true. The pawn clearly makes this true by virtue of being light and not taller than itself. However, the queen and also the knight satisfy the antecedent condition. They're both light and not taller than themselves, but they are not pawns. So true, false, right? Both of them are counterexamples, making the whole proposition false. Okay, and the reasoning we just provided on the previous one will give us the answer to this one quite quickly. For all, so again, for all x, if x is light and not taller than itself, restricting the antecedent condition to the queen, knight, and pawn, then it is not the case that if x is pawn or x is knight, then x is queen. So here, just bracket the negation for a second and evaluate the conditional. If x is pawn or x is a knight, then x is queen, clearly false, making the negation of the conditional true. Hence, for any time the antecedent is true, the consequent is true, making this true. All right, next one, for all x and for all y, if x is equal in power to y, and it's not the case that x is identical to y. So the only things that satisfy the antecedent condition, as we noted before, are bishop and knight. And of course they could inhabit both the x or the y, so you got to be willing to switch those around if necessary. So for all x and for all y, if x is equal in power to y, and it's not the case that x equals y, then if it's not the case that it's the bishop, then it's the king, right? K stands for king here, not knight. You might have been prepared for knight to make this true, but in fact it ends up being false, right? So if we put knight in for x and bishop in for y, that makes the antecedent true and the consequent false, because knight makes it's not the case that x equals bishop true, but knight is not king, making the consequent false. So true, false, false. So for all x and for all y, if x is adjacent to y, then y is adjacent to x. That's true simply by virtue of the meaning of adjacent. Don't even really have to look at the model. If this had been a biconditional, would it have been true? And the answer here is yes, because a biconditional is true whenever both sides of the biconditional always have the same truth value. So if x is adjacent to y is true, y is adjacent to x is true, but if x is not adjacent to y, in other words, if x is adjacent to y is false, then y is adjacent to x is also false. That may sound like a pretty complicated explanation for something that's pretty obvious, but that's kind of the way semantics is. Okay, for all x, there exists a y such that x is adjacent to y. So this is saying that everything has something that is next to it. Obviously true. For all x, there exists a y and there exists a z such that y is adjacent to x and z is adjacent to x. So if you learned your lessons from the last review about the nature of the existentials and what makes them true or false when two or more are used, you'll get this one right. What's the answer? The answer is true, right? Now, why is it true? Because this doesn't say that everything has two different things that are adjacent to it, right? It says there exists a y and there exists a z, and y and z could be the same thing. So if you're looking at the terminal pieces, you've got the queen and the pawn, and of course there are not two different pieces adjacent to them, but say in the case of the rook, right, the rook could be both y and z. And that of course is why the next one is what? False. Why is that? Because now we have the stipulation that y is not identical to z. So for all x, there exists a y and there exists a z, such that y is adjacent to x and z is adjacent to x, and it's not the case that y is equal to z. So this is false because this is a conjunction, all of which conjuncts have to be true for every value of x. So if we plug pawn in for x, then it is not the case that there exist two different things next to the pawn that are adjacent to it. Okay, I should point out one other thing about this formula, and that is you'll notice that it's not a woof, but at this point we are now going to be adopting the convention that when you have strings of conjunctions or strings of disjunction, it is permissible to drop the internal parentheses. You are by no means required to do so, but the reason for this unofficial convention is that the parentheses within, whether they were here or here, would not affect the truth value of this formula. So if you're starting to get a little bit comfortable with reading these, then maybe even something like this formula is surprisingly easy to understand. So for all x and for all y, if x is adjacent to y and x is equal in power to y, and it's not the case that x equals y, so that can clearly only be the knight and the bishop, or the bishop and the knight, even without this non-identity stipulation, since nothing is adjacent to itself. So for all x and for all y, if x is adjacent to y and x is equal in power to y, and it's not the case that x equals y, then x is the bishop, or x is adjacent to the rook. So no matter, since only the rook and the bishop have the power to make this, the antecedent, true, no matter how you instantiate x, it's going to have to be to the bishop, or it's going to have to be to the knight, which is, of course, adjacent to the rook. So if you put the bishop in for x, then you satisfy x equals the bishop, that part of the disjunction, making the disjunction true. If you put the knight in for x, then you satisfy the other disjunct, making the disjunct true again. So true. Okay, for all x, there exists a y. For every x, there exists some y, such that x is adjacent to y, and x is weaker than y, or x is taller than y. So we know that everything has something adjacent to it, so the first conjunct is satisfied by everything, but then the question is whether the thing that is adjacent, or a thing that is adjacent, is either weaker than y or taller than y. So this one's tedious because you have to look at every possibility. Look at the king. The queen is definitely weaker, so the disjunction is satisfied there. Look at the queen. The king is definitely taller, and also the bishop is weaker, so the disjunction is over-satisfied there. Look at the bishop. Yes, in both cases, over-satisfied. Look at the knight. The bishop is taller. Look at the rook. The pawn is weaker. Look at the pawn. The knight is taller. Okay, so every single one satisfies the disjunction, and the first conjunct. So both conjuncts are satisfied, so true. Okay, it's not the case. It is not the case that there exists an x, exists a y, and exists a z, such that x is adjacent to y, and y is adjacent to z, and x is also adjacent to z. So this is clearly, let me back up a little. When you're going to evaluate a negated proposition, the best thing to do is ignore the negation and determine whether the non-negated formula is true, right? And then just flip the truth value. So if we're thinking about three distinct objects, which isn't necessary, but we do, which isn't necessarily the case, but we do have to consider that possibility. If we're thinking about three distinct objects, they would have to be all in a row. And of course, if x is adjacent to y and y is adjacent to z, then there is no way that x is adjacent to z. It will always be separated by y. So what you have to think about is a situation where they're not all distinct. So the easy one is think about when x, y, and z are all the same thing, right? So then it would have to be x is adjacent to y and y is adjacent to z, and that's automatically false because nothing is adjacent to itself. So again, making the non-negated proposition true and the false and the negated proposition true. So then what about when one of them is, say, both y and z, so that we are only talking about two different pieces? So let's let king be both x and z, for example. So then the queen being y would make x is adjacent to y true, and it would also make y is adjacent to z true. because the king is both x and z, but x is adjacent to z would mean the king is adjacent to itself, which is false, making the conjunction false. So again, making the negated statement true. And this example would work for every single situation where we made x and z identical. Okay? So no matter whether they are all non-identical, all identical, or 2 is identical and 1 is not, you still get false for the non-negated proposition and therefore true for the negated proposition. So for all x and for all y, if it's not the case that x is adjacent to y, then x is weaker than y or y is weaker than x. So pick any 2 non-adjacent things and you will see that they are not equal in value or strength, and therefore this is true. Did that sound right to you? Well, it sounded right to me too, but it's not right. This is actually false, and can you stop and think about it and tell me why? The answer is because everything is not adjacent to itself, right? So x and y could be identical, but of course x is neither weaker than y nor is y weaker than x. Okay? So again, those are tricky, but you always have to be aware of this problem of self-reference. This is a computational issue just as much as it's a logical issue. There exists an x such that x is identical to the bishop. Well, that's certainly true. First conjunct satisfied. And for all z, if z is identical to the bishop, then z is equal in power to king, not knight, king. And that is clearly false. So true and false means false. So there exists an x such that for all y, if x is identical to the pawn, then it's not the case that y is stronger than x. So there exists an x such that for all y, if x is identical to the pawn, then it's not the case that y is stronger than x. Now, this is one of those strange ones where we might struggle for the meaning of it. It's an existential, it's a conditionalized existential. So there exists an x such that if it's something, then something else, a relatively unusual English sentence. So as I've said before, sometimes it helps to convert this into the logically equivalent disjunction, which would mean turning the conditional into an or and negating x is identical to p. So then it just says there exists an x such that for all y, it's not the case that x is identical to p, or it's not the case that y is stronger than x. You just have to satisfy one of the disjuncts. In order for this to be true, you need to just do it one time because it's just saying there exists such a... So the king is not the pawn, right? So the disjunct is satisfied, making the whole thing true. In fact, everything makes this true except the pawn itself. So true. Now, if you got a different answer than this one, it might have been because you were maybe thinking of both of the quantifiers as being universal. So if we back up a little bit here, right, we could ask, what would the truth value have been if we said for all x and for all y. If x is the pawn, then it's not the case that y is stronger than x. Well, everything that is not the pawn makes the antecedent false, making the whole thing true. So we only need to think of a situation where x is the pawn. Then we could ask, is it the case that for all y is stronger than x? And the answer is no, because the pawn is not stronger than the pawn. So the non-negated formula would be false, making the gave formula true. So again, it ends up being true. So either way, it ends up being true. So the next one, there exists an x such that for all y, it's not the case that y is stronger than x if and only if x is identical to p. So here you're looking for some value of x that would make the universal true. Now you might think that the best way of approaching this would be to go for the pawn, since pawn equals pawn is always true. But since everything but the pawn is stronger than the pawn, that would only be able to make the biconditional false, right? It's true, false for everything, every value of y except the pawn. And it's fine, that's good information, but that doesn't make it false necessarily, because there still might be something that makes it true, right? So suppose we stuck, say, the knight in for x. So then we get for all y, it's not the case that y is stronger than the knight. Well, that is false, because there are things that are stronger than the knight, if and only if the knight is identical to the pawn. But the knight is not identical to the pawn. So if we stick the knight in for x, then when we evaluate the universal, we get false and false. And this, remember, makes the biconditional true. All right. Okay, the next one, for all x and for all y, x is adjacent to y. Well, that's clearly false, right? So this is a disjunction, right? That's the main operator. And so the only hope of this turning out to be true is if the conditional is true. So the conditional says if it's not the case that x is light and y is light, in other words, one of them has to be dark, right? Then x is dark and y is dark. Well, that's clearly going to be false, because only one of them has to be dark, right? So formally, if we stick the pawn in for x and the rook in for y, then x is light and y is light is false, making the negated antecedent true. But they are not both dark, making the consequent false. So true, false, false. So both sides of the disjunct are false, making the entire proposition false. For all x and for all y, x is taller than y if and only if x is adjacent to y. We'll make this false by finding one instance where the left-hand side of the biconditional is true and the right-hand side is false, or vice versa. So the king is, in fact, taller than the pawn, but the king is certainly not adjacent to the pawn, right? So it is not the case that for all x and for all y, x is taller than y, if and only if x is adjacent to y. All right, for all x, for all y, for all z, if x is adjacent to y and x is adjacent to z and x is light and y is light, then x is identical to bishop or x is identical to rook. Well, if you think about this one, you could actually ask yourself this: when is it the case that x is adjacent to y and x is light and also y is light, right? So for a moment, neglect that fourth conjunct. When is it the case that two things are adjacent to each other? So nothing's adjacent to itself, so you can rule that out. And one of the things is light and the other is also light. And the answer is never, right? So since no two things are adjacent to each other and both light, then the antecedent condition is always false, making the statement false, right? Oops, no, right? True. When the antecedent of a conditional is false, the entire statement is true. Okay, and finally, for all x and for all y, x is stronger than y if and only if x is taller than y. So in order for this to be true, both sides of the biconditional would have to always be false or always be true. So if you found any example where one side is true and the other is false, then the universal would have to be false. So if you look at the picture, the rook is stronger than the knight. It's also stronger than the bishop and quite obviously shorter than the bishop. So put the rook in for x and the bishop in for y, and you get x is stronger than y, true, but x is taller than y, false. So there's your exception to the universal generalization, making this false. Okay, so semantics and predicate logic is a bit tricky sometimes, a bit tedious, really forces you to develop a strong understanding of the meaning and therefore the truth conditions of predicate logic formulas.